Okay, so let's imagine that you have a cylinder. Okay. Cylindrical pipe. Okay. let's analyze the heat transfer happening through this pipe, which has a contact with fluid A in the middle and fluid B surrounding it. Okay. And fluid B has a temperature of TB and has a heat transfer coefficient HB. And the fluid A has a temperature of TA and heat transfer coefficient of HA. Okay. And imagine that the fluid A is flowing through the pipe and fluid B is flowing outside of the pipe. Okay. And imagine that TA, fluid A, is hotter than fluid B. Well, basically, you want to cool down the TA using the stream B. Okay, so there's going to be some heat transfer between the two. Okay, let's focus on a section where TA or TB does not change appreciably. You can think about this like a plug flow reactor, which is kept at a constant temperature. So you can actually use like an outside fluid to cool down the stream so that it's at a constant temperature of TA. Or you can actually focus on a really small section of the pipe, sufficiently small, for example, length L, such a way that the temperature of A does not change along the L appreciably. Okay. So let's do the shell balance. So let's. I want to find out the temperature gradient along this pipe, right? So for this, I need to do shell balance, right? And by the way, let's write down the problem more clearly. So the pipe has a conductivity K, and let us find a temperature profile along the R direction within the pipe. B, let's find out the heat transferred rate of heat transferred, let's say. Rate of heat transferred per unit length of the pipe. In other words, Q dot over L is equal to question mark. So let's find these two things. Okay. Can everybody hear me?
Yes.
Okay, great. Any questions so far? No? Okay. So this is a like a very nice engineering problem where you need to estimate the heat transfer from one fluid to another to see whether the flow conditions of the fluid B or fluid A is sufficient to obtain a sufficient amount of heat transfer rate, for example. Okay. And it also helps us learn about the shell balance in more detail. So let's take a cylindrical shell within the pipe at a distance r, and the flux getting in the shell, let's call it QR at r, and the flux coming out is QR at r plus delta r. And if you do the shell balance, you're all familiar with in minus out plus generation is equal to accumulation. Let's imagine that it's steady state, so it's 0. And let's imagine that there is no heat generation within the pipe. So there is a very important point here. Even if there is a reaction in fluid A, even if there is some reaction happening in fluid A, the heat generation within the pipe is 0. There might be heat generation within the fluid A, but when you do the shell balance for the pipe, you should take it 0. But if I actually connect it to an electrical circuit and generate some heat within the pipe, then it would not be 0. So that you should be really careful about that. You should be careful about where is your shell. I'm sorry. Where is the shell? And what are the conditions within the shell? Okay, and the amount coming in is the heat flux QR times the area through which the heat flux is passing. It's basically 2 pi r times L. Basically, my QR is penetrating through this shell, which has a length of L, a radius of r. So that folded region has an area of 2 pi RL. And you calculate this for r is equal to r minus the out one is QR 2 pi r L at r plus delta r is equal to 0. Now, a very important point here is that you can ask, how do you know that the QR is along the plus r direction? Maybe because maybe the TA, like TB is hotter than TA. Maybe the heat is flowing from the B fluid side to the towards inside. Well, you can say, although it's given in the problem, but TA is larger than TB, you can always take it, even in the case where TB is larger than TA, you can take it as if QR is coming out, because the sign of the QR is going to tell you whether it's going out or getting in. So you should always, I mean, it's very convenient to take the QR along the plus R direction, or QX to the plus X direction, and QY towards the plus Y direction. So take it as if it's positive, and then whatever the result comes out, you can actually argue whether it's towards inside or outside. Okay, so it's a good practice to take the QR along the plus R direction. Okay. Okay, because it's going to have a signed quantity. Now, if you divide by delta R, and take the limit as delta R goes to 0, you find the following: minus derivative of QR 2 pi RL is equal to 0. Well, the 2 pi and L are constant, but R is not. So d over dr, QRR is 0. From here you find QRR is equal to constant. Let's call it C1. And thus QR is equal to C1 over R. Okay. And you can write down the Fourier's law to find out the temperature distribution. It's basically minus K of the pipe dt over dr is equal to QR, which is C1 over R. Okay. And then you solve for dt is equal to minus C1 over K R dr. And then you take the integral, both sides. T comes out to be equal to minus C1 over K R squared over 2 plus C2, right? And you need two boundary conditions to solve for C1 and C2. Boundary condition 1, at R is equal to, let's call it R1 and R2. Let's call this R1. And let's call this R2. At R is equal to R1, let's call the temperature is equal to T1. And then from here you get T1 is equal to minus C1 over K R1 squared over 2 plus C2. And the boundary condition 2, at R is equal to R2, T is equal to T2. Although the T1 and T2 are not given, you can actually write it in terms of T1. Instead of using C1 and C2, you can actually solve for C1 and C2 in terms of T1 and T2. And then try to find out what is T1 and T2 with respect to the fluid temperatures, TA and TB, that we're going to do in another step. So T2 is equal to minus C1 over K, R2 squared over 2 plus C2. So you can actually solve these two equations. First, you can subtract, for example, one from the other, and you find T1 minus T2. Let's say subtract. So let's go more clearly. Let's call this equation 1, this equation 2. Subtracting 2 from 1 yields T1 minus T2 is equal to minus C1 over K, say C1 over 2K, R1 squared minus R2 squared. From here, the C1 comes out to be 2K T1 minus T2 divided by R1 squared minus R2 squared, minus of it, basically. Or you can play with the T1 and T2, the location of the T1 and T2, or you can just say minus. Okay, that's C1. Knowing C1, you can actually write down the C2 using 1 and knowing C1, we get T1 is equal to minus C1 over K. I can just write it as like 2 times T1 minus T2, R1 squared, R2 squared. If there's anything that you cannot follow, please like stop me at that point and I can clarify. Times R1 squared over 2. Well, I can get rid of the 2's as well. So plus C2. So you can solve for C2 is equal to T1 minus T2 R1 squared divided by R1 squared minus R2 squared. That's C2. And if you plug in these into the equation, the temperature profile looks, this temperature profile, it's going to look T is equal to minus C1 over K, well, actually minus C1 over 2K, you can write as T1 minus T2 divided by R1 squared minus R2 squared, R squared plus C2, which is this number, but I'm going to write it in the other order, minus T1 minus T2 over R1 squared minus R2 squared, R1 squared plus T1. Rearranging gives T is equal to T1 plus T1 minus T2 divided by R1 squared minus R2 squared, in parentheses R squared minus R1 squared. So that's your equation. Check the units. Kelvin on the left-hand side, and you should get Kelvin on the right-hand side. And then check the BCs. At R is equal to R1, you get T is equal to T1. That's correct, right? This becomes 0, and you get this only. Let's check the other BC. At R is equal to R2, if you plug in R2 here, then these two cancel, and then you get this and this, and these, yeah, I made a mistake here then. T1, yeah, I made a mistake here, see. If you plug in R2, oh, no, I didn't make a mistake, because if you plug in R2 here, then this becomes minus of the denominator, so you get -1 if you cancel the 2. So this is minus T1 plus T2, and you cancel these 2, and then you come up with the T2, which makes sense. Okay, so that's correct. But I could have made a mistake, so T is equal to T2, that's a check mark. Okay, so that's my temperature profile with respect to T1 and T2, but you should actually find out the T1 and T2 in terms of TA and TB, right? How to relate T1, T2 to TA and TB. We are going to make use of the Newton's law of cooling. We're going to write down Q is equal to okay, so let's say QR at R1 times 2 pi R1 L, it's the area, or let's just write down the Newton's law of cooling. QR at R1 must be equal to HA, because it's the fluid A which is inside, times TA minus T1. Now, this is very important. It's not because TA is larger than T1. It's because I'm taking the QR direction towards outside of the pipe. That means I should actually pretend as if TA is larger than T1, and TA is not necessarily larger than T1. So it's just because on the direction. So when the TA is larger than T1, I should get a positive value. When TA is smaller than T1, I should get a negative value, which is in the correct radial dimension, right? When A is larger than 1, the flux should be outside.
So I have a question.
Sure, yeah, go ahead.
So had we written T1 minus TA, and ultimately the signs of our answer would have told that our assumption was wrong. So there's no issue in writing, like by mistake, if I write T1 minus TA, I still would get the right answer, right?
I don't think so, because in all, look, there is a reason why we actually write down, for example, QR is equal to minus K dt over dr, for example, right? Because we say that if the temperature is increasing, right, I should have the QR towards the negative R direction. I should get a negative sign. That's why. And you should always take the QR, like treat the QR as a vector quantity, and you should basically say if the flux is really outside, right, your Q is positive, and if your flux is inside, your Q is negative. Okay, don't actually take the other way around. That's very important. The only important thing here is that the QR is a vector quantity. If it's towards plus R direction, take it as a positive value. If it's towards negative R direction, it should take a negative value. Otherwise, your Fourier's law would be wrong. I mean, you should restate your Fourier's law in another way. Does that make sense? That's the convention that we are using. And you should be consistent with that convention. If you're going to use some other convention that towards minus R direction, you call the Q positive, and towards the R direction, you call it negative, then you should come up with your own equations and should not use the Fourier's law, but the plus version of the Fourier's law, which I don't recommend you to do. Does that make sense?
Yeah. Thanks.
Okay. Good. Excellent question. Thank you. So that's the Newton's law of cooling. Now, okay, and we know that the well, actually, can I write another equation? Because I mean, this doesn't give me by itself any relation between TA and T1, because I don't know the QR at R1. But I know that here I found from the shell balance, whatever the shell balance gives you a very important information. And it tells you that the QR times R is constant. See, the QR times R is constant, right? So you can say that QR at capital R1 times capital R1 is equal to QR at capital R2 times capital R2 within the pipe, right? So you can use any R to calculate this, and it's going to be a constant, right? And you can actually relate it to the Q, the heat transfer rate. So you can say that the heat transferred along the pipe is going to be equal to the heat flux QR, right? Let's imagine, let's calculate that R is equal to R1 times the area, the 2 pi R1 times L, correct? Or you can write it as QR at R2, 2 pi R2 L. And please note that this thing is a constant. So these are constants. So that's why the Q is constant along the pipe. So whatever is actually coming in here, oops, sorry. Whatever is coming in here is coming out because there's no generation. That's the reason why we get the QR times R constant. And so Q is constant. And you can actually write down the Q over L in terms of this constant. QR at R1 times R1 times 2 pi. Or you can take the 2 pi out. I mean, to the other side. Okay. And you can call this quantity Q over 2 pi L, which is constant, as the shell balance gave you, right? What does it mean? It means I can write this equation as QR at R1, but it's basically Q over 2 pi L times R1, right? So you can actually write down the T1 in terms of Qs and TAs. Okay. So TA minus T1 is equal to Q over, let's take the HA to the other side, 2 pi L R1 HA. Okay. Why did I write it in this form? Why did I actually write down temperature differences? One thing is because I love to write down the temperature differences. The reason is I like to add up the temperature differences and cancel some of them and find out the difference of the terminal temperatures, as we did in the class, right? Because I want to write down TA minus T1, and then T1 minus T2, and then T2 minus TB, and then I want to add up those, and I want to get rid of all, and I want to get the difference between the TA and TB. That's what I want to do. When you write down the temperature differences with respect to other quantities, then your equation becomes really easy to solve. Okay, this is a very important trick I recommend you to do. Similarly, let's write down the T1 minus T2. Well, actually, we found the T1 minus T2, right, did we? Let's see. T1 minus T2. Yeah, but yeah, okay, so here's the thing. So we're going to use the following. So we have the T1 minus T2 here, right? And it says that we should know the C1 for this is equal to minus C1 over 2K R1 squared minus R2 squared, correct? But now I'm not allowed to use the C1 because if I plug the C1 here, that's going to be like T1 minus TA is going to be equal to T1 minus TA. That doesn't give me anything, but I'm going to solve for C1 using this equation, using the QRs. Okay. So as you can see, the C1 is nothing but the same C1 as the QR times R. C1, right? So instead of C1, you can write down QR times R. That's the same CR which actually gave us the the rest of the equations, right? So let's say let's plug it in here, and you get, why does this not, oops, what's going on? Okay, there, good. Then this is equal to minus QR at, or maybe, okay. So as you can see here, have a look at this thing. Have a look at that thing. That C1 is nothing but this Q over 2 pi L, right? So I can just equally well write this here, right? So that's going to be Q over 2 pi L times 2K. It's the same constant. This is the C1, basically, that we had used. And times R1 squared minus R2 squared. There you go. We are getting close to that. Now, here I wrote down the difference in terms of Q's. Here also I wrote down the difference in terms of Q's. Let's call this 1. Let's call this 2. And similarly for T2 minus TB, as in this equation, we get Q divided by 2 pi L R2 this time, because the surface has the radius R2 there, and HB this time, because your outer fluid is HB instead of HA. So it's basically, you're going to get the same equation with the same arguments, but for the fluid B. So this is your third equation. So let's add 1, 2, 3. Add 1, 2, and 3 to get TA minus TB is equal to, you have this Q over 2 pi L's. Let's take to 2Q over 2 pi L parenthesis. And then you have 1 over R1 HA plus, let's do, plus. This is minus, but I'm going to make it plus by actually switching these R1 and R2. So 1 over 2K R2 squared. Let's do it this way. R2 squared minus R1 squared divided by 2K plus 1 over RB HB. Right? There you go. Now, you have the temperature difference related to Q, so you can basically do it the other way around. Write the Q in terms of temperature differences. So the Q over L, basically, the heat transfer rate per unit length, comes out to be equal to 2 pi. I want to just keep the 2 pi in the denominators. TA minus TB divided by 1 over 2 pi R1 HA plus R2 squared minus R1 squared over 4 pi K plus 1 over 2 pi RB HB. There you go. So we found the heat transfer rate per unit length with respect to the fluid temperature. And if you think about this as like flux is proportional to the delta T divided by resistances, this gives you the heat transfer resistance due to the fluid A pipe interface. This gives you the heat transfer resistance due to the pipe skin, and this is the heat transfer resistance. So you can actually add those resistance, and you can show this as like sum of the three resistances, R1, R2, R3. This is your R1, this is your R2, this is your R3. Okay, in terms of the electrical analogy. Okay, so that's it. Any questions so far?
I have a question.
Sure.
In the TA minus TB, you wrote RB. Should that be R2?
Oh yeah, excellent.
And then it's also in the Q over L.
Yep. And who is correcting this?
Cameron.
Cameron, excellent. Thank you. Okay. Any other questions or corrections or comments? Yeah. Okay, there's one thing we're missing. What are we missing here? Any suggestion?
Temperature profile evaluation.
Exactly. We got the temperature profile, but you're right. The temperature profile has T1s and T2s, but it's missing the TA and TB. So instead of T1 and T2, you should actually write it in terms of TA and TB, right? And what comes to the rescue is basically you can write down. Okay, so you can either like use this equation and this equation to write the TB and T1 and T2 in terms of TA and TB and plug into this equation, which is going to take a lot of time. Okay, what I recommend you to do would be basically okay, so here the method I would suggest is just give me a second. Yeah, so we can actually write down the C1. Have a look at this equation. So let's go back to T profile, right? We said that the temperature profile is minus C1 over K, R squared over 2, or 2K here, plus C2. And we can use the boundary conditions again, but in terms of TA this time. So you can say at R is equal to R1, the flux Q1, flux QR will be equal to HA times TA minus T1, right? Yeah. And if you calculate the QR is nothing but from our previous analogy, C1 over R. C1 over R is basically C1 over R1 HA TA minus T1. Okay, that's one equation. I guess it's okay. So let's do it this way. So let's get rid of this.
If you if you add 2 and 3, I think by that way we can get T minus T1 first. Okay.
One
Like,
and what?
If we add the second and third equation,
Yep.
we will get T1 in terms of TB.
Yeah.
Directly. And we already know what is T1 minus T2. So we can substitute that in this TR function that we have got earlier on.
Yeah. Yeah. Yeah, you can do that. Or you can just here we can just plug in the C1, right? We have found the C1 here. We have found the C1 in terms of Q's, right?
Mm-hmm.
Yeah, and it's Q over 2 pi L. Q over right? And as you said, yeah, we can get the T2, right? Or maybe T1, doesn't matter. T1 is equal to minus Q over 2K 2 pi L, capital R1 squared plus C2. We can subtract to get T minus T1 is equal to minus Q over 4K 2 pi L, sorry, 4K pi L. Right? And you can write down the T1 minus TA from the equation 1. It's going to be the minus of this thing, minus Q over 2 pi L R1 HA, 2 pi L R1 HA, correct? Now you can add the 2. T minus TA is equal to minus Q over 2 pi L. Let's take the 2 pi L parenthesis. And it's going to be 1 over 2K plus 1 over R1HA. Correct? There you go. So you have the temperature profile. So since you already know the Q, that's no problem. So you can actually calculate the Q in terms of TA and TB. That means you actually know the Q from the given variables. So that's your temperature profile. Okay. Good. Any questions so far? Where is my R here? There's one thing I'm missing, right? Oops. Oh. You're not correcting me. So this one, if you subtract the 2, right, you get R squared minus R1 squared here. Okay. Yep. Yeah, I was saying, oh, where is this lowercase r, which t depends on? Okay, is that clear? Everybody? Any questions? Let's check whether we made a mistake. Check units. So this is watt per. No, it's just watts. Yeah, right. This is, yeah, that's watt. This is meters. These are unitless. This is meter square. This is watt per meter Kelvin. Okay. No, it doesn't look right. Where did we mess up? Let's check this thing. This is watt per meter Kelvin. No, I have, okay, I have something missing here, I guess. Either here or here. C1, how did I plug in the C1? The C1 is, the C1 looks correct, right? Q over 2 pi L. Okay. Okay. So let's check the units of C1. C1 should have the units watt per meter squared. Watt per meter squared. No, watt per meter. The C must have units for watt per meter, because if you divide by meter, you should get watt per meter square, the C1, correct? Again, here it's watt per meter. Here, this C1, watt per meter divided by watt per meter Kelvin. But you have the R there. I mean, can you follow? I mean, I think there's some problem with the units going from here to here. The C1 has the units of watt per meter, we said, and okay, this is watt per meter. This is watt per meter Kelvin. So get Kelvin, but you have R square here. Oh, you know what? That's okay. Nobody has warned me about this. Okay, so this is all wrong. So here, the temperature distribution, we don't have this. We have the logarithm, right? T is going to be equal to minus C1 over K logarithm of R plus C2. That makes sense now. Okay. So because the unit did not actually make sense. Okay, now it should make sense. Good. Let's correct these. Okay. Logarithm of R1 plus C2. And I mean, this is not R. That was the problem. This is 1 over R. And the integral of 1 over R is logarithm of R. So we messed up. R2. And this is going to be logarithm of R1 over R2. Can you follow now? Okay. Okay, let's okay, so that's okay. So let's divide by negative 2k. You get t1 minus t2 over logarithm of R1 over
I have
R2.
a question.
Sure.
In
Yep.
the T1 minus T2 expression, shouldn't the 2k just be k?
Yeah, this time, yeah, it was not R, so it's not R squared over 2 now. Yeah, it's just a logarithm of R. Exactly. Thank you for correcting that. Okay, there you go. And then now we have logarithm of R1 plus C2, correct? And then C2 comes out to be T1 minus oops. Yep. There you go. So let's erase this part. So you can write down the t is equal to whatever the C1 and C2 is, so you can plug in there. Okay, good. Let's erase this. And then let's go back to this, how to relate T1, T2, blah, blah. So there's nothing wrong here, I guess. There's nothing wrong in here. There's nothing wrong in here, correct? And this is correct. These arguments are all valid still. This is correct. But here, let's write down the T1 minus T2 back again and plug in the C1 there. Minus C1 over K, logarithm of R1 over R2. Yep, and the C1 is nothing but Q over 2 pi L, Q over 2 pi L, and you don't have the 2K this time. And there you go. You're almost there. Right? And then T2 minus TB. This should be valid because it's based on this one. It's very similar to the equation 1. Okay. Now we add 1, 2, and 3. The middle term was the problematic one. We still get this Q over 2 pi L there. But the middle term, let's erase it. Let's make it 1 over K, right? Logarithm of R2 over R1, let me write, because minus logarithm of A over B is the plus logarithm of B over A. So you can actually play with the position of the R1 and R2. So that's it. And let's correct this too. Logarithm R2 over R1 divided by 2 pi K. There you go. So we did it. Okay, now the units should make sense. Let's go back to the T profile we said. Let's plug in the C1 this time, which is Q over, so you don't have this and you don't have these. It's basically minus C1 over K, logarithm of R, right? Okay, logarithm of R. Okay. And we plug in R1. There you go. I can't believe we did it. Okay, good. So this is 2. Logarithm of R over R1. Because if you subtract ln R1 from ln R, you get ln R over R1. And this has the correct units, right? Now. So let's see, T1 over TA. Where was the T1 over TA? Yeah, that was correct. T1 over TA. No, the T1 over TA. Q over 2 pi L R1 HA. So you don't have this term. Good. Right? Okay. So let's erase it. We got rid of the problematic part. So negative Q over 2 pi L. Okay, so logarithm of R over R1 divided by K plus okay, 1 over R1 HA. There you go. Now you check the units, you should see that it's correct. Yeah, the units should be correct right now. If you want, you can check. And let's do a couple of tests. This is your temperature profile. Check units. At r is equal to r1, what happens is this becomes 0, and you get t minus ta as in here, ta minus t1. That should be correct. And you can check this for yeah, you don't need to check it for anything else. I think this should be correct. Any questions so far? Now, you probably realized something really amazing, right? Today. So one nice thing we realized today is no matter how experienced you are in this field, you can always do mistakes, but the dimensional analysis actually helps you whether you made a mistake. Remember the parts that the point where I understood that I made some mistake was right after I checked the dimensionality of the equation, and I saw that it doesn't actually make sense. Then I saw there's something wrong with this equation, and I actually went back and found out exactly where I made the mistake. So that's a very strong recommendation to you. Always check the units, always check the formula, whether it makes sense. Always look at the limiting cases, whether your formula actually makes sense for limiting cases.